Hello friends, warm welcome in this video that is the history of immunity. Friends, whenever someone asks us what is the meaning of immunity and we try to find out the answer, can we reach at the conclusion that immunity is the vast defensive mechanism of a multicellular organism against invading pathogens and cancer. The immune system evolves to protect multicellular organisms from pathogens. This is a highly adaptable system and defends the body against invaders and diverse as the teeny 30 nanometer intracellular virus that causes polio and as large as the giant parasitic kidney worm Diptheria renal, which can grow to over 100 cm in length and 10 mm in width. This diversity of potential pathogens requires a range of recognition and destruction mechanisms. Vertebrates have evolved complicated and dynamic network of cells, molecules, and pathways. Although elements of these networks can be found throughout the plant and animal kingdoms, the fully functional immune system involves so many organs, molecules, cells, and pathways in such an interconnected and sometimes circular process that it is often difficult to know where to start. The study of immunology has produced amazing and fascinating stories where host and microbe engage in battles waged over both minute and millennia. But the immune system is also much more than an isolated component of the body, merely responsible for search and destroy missions. In fact, it interleaves with many of the other body systems, including the endocrine, nervous, and metabolic systems, with more connections undoubtedly to be discovered in time. Finally, it has become increasingly clear that elements of immunity play key roles in regulating homeostasis in the body of healthy balance. Friends, when we try to find out the literary meaning of immunity, then we reach at the conclusion that this word immunity is derived from the Latin word immunis, which means exempt. Immunity is a state of protection from infectious disease. The discipline of immunology grew out of observations that individuals who had recovered from certain infectious diseases were thereafter protected from the disease. Perhaps the earliest written references to the phenomena of immunity can be traced back to Thucydides, the great historian of Peloponnesian War. In describing a plague in Athens, he wrote in 430 BC that only those who had recovered from the plague could nurse the sick because they would not contract to the disease a second time. Although early societies recognized the phenomena of immunity, almost 2000 years passed before the concept was successfully converted into medically effective practice. The first recorded attempt to deliberately induce immunity were performed by the Chinese and Turks in the 15th century. They were attempting to prevent smallpox, a disease that is fatal in about 30% of cases and that leaves survivors disfigured for life. Reports suggested that the dried crust derived from smallpox pustules were either inhaled or inserted into small cuts in the skin, that is a technique called as variolation, in order to prevent this dreaded disease. In 1780, Lady Mary Wortley Montagu, the wife of the British ambassador in Constantinople, observed a positive effects of variolation on the native Turkish population and had the technique performed on her own children. The English physician Edward Jenner later made a giant advance in the deliberate development of immunity, again targeting smallpox. In 1798, intrigued by the fact that milkmaids who had contracted the mild disease cowpox were subsequently immune to the much more severe smallpox, Jenner reasoned that the introducing fluid from a cowpox pustules into the people, that is inoculating them, might protect them from the smallpox. To test this idea, he inoculated an 8-year-old boy with fluid from a cowpox pustule and later intentionally infected the child with smallpox. As predicted, the child did not develop smallpox, although this represented a major breakthrough as one might imagine. These sorts of human studies could not be conducted under current standards of medical ethics. Jenner's techniques of inoculating with a cowpox to protect against smallpox spread quickly throughout the Europe. However, it was nearly hundreds of years before the technique was applied to other diseases. As so happens in science, serendipity combined with astute observations led to the next major advances in immunology, the induction of immunity to cholera. Louis Pasteur had succeeded in growing the bacterium that causes fowl cholera in culture and confirmed this by injecting it into chickens that then developed feral cholera. After returning from a summer vacation, he and colleagues resumed their experiments, injecting some chickens with an old bacterial culture. The chickens became ill, but to Pasteur's surprise, they recovered. Interested, Pasteur then grew a fresh culture of the bacterium with the intention of injecting this lethal brew into some fresh, unexposed chickens. But as the story is told, his supply of fresh chickens was limited, and therefore he used a mixture of previously injected chickens and unexposed birds. Unexpectedly, only the fresh chickens died, while the chickens previously exposed to the older bacterial cultures were completely protected from the disease. Pasteur hypothesized and later showed that the aging and weakening the virulence of the pathogen and that such a weakened or attenuated strain could be unleashed to provide immunity against the disease. He called this attenuated strain a vaccine from the Latin word vacca, which means cow, in honor of the genus works with the cowpox inoculation. He extended these findings to other diseases, demonstrating that it was possible to attenuate a pathogen and administer the attenuated strain as a vaccine. In now classic experiments performed in the small village of Pustules in 1881, Pasteur first vaccinated one group of sheep with anthrax bacteria, Bacillus anthracis, that were attenuated by heat treatment. He then challenged the vaccinated sheep along with some unvaccinated sheep with a virulent culture of anthrax bacillus. All the vaccinated sheep lived and all the unvaccinated animals died. These experiments marked the beginning of the discipline of immunology. In 1885, Pasteur administered his first vaccine to a human, a young boy who had been bitten repeatedly by a rabid dog. The boy, Joseph Mister, was inoculated with the series of attenuated rabies virus preparations. The rabies vaccine is one of a very few that can be successful when administered shortly after exposure. As long as the virus has not yet reached the central nervous system and begun to induce neurologic symptoms, Joseph lived and later becomes a caretaker at the Pasteur Institute, which was opened in 1887 to treat the many rabies victims that became to flood in men where a Pasteur success spread. It remains to this day an institute dedicated to prevention and treatment of infectious diseases. The emergence of the study of immunology and the discovery of vaccine are tightly linked. The development of effective vaccines for some pathogens is still a major challenge discussed. However, despite many biological and social hurdles, vaccines has yielded some of the most profound success stories in terms of improving mortality rates worldwide, especially in very young children. In 1977, the last known case of naturally acquired smallpox was seen in Somalia. Early Maow Maalin was a Somali hospital cook and health worker from Merca, who is the last person known to be infected with a naturally occurring smallpox. This dreaded disease was eradicated by universal applications of vaccine similarly that used by Jenner in 1970s. One consequence of eradication is that universal vaccination became unnecessary. This is a tremendous benefit as most vaccines carry at least a slight risk persons vaccinated, and yet in many cases every individual does not need to be immune in order to protect most of the population. As critical mass of people acquires protective immunity either through vaccination or infection, they can serve as a buffer for the rest. This principle is called as herd immunity, works by decreasing the number of individuals who can harbor and spread an infectious agent, significantly decreasing the chances that susceptible individuals will become infected. This presents an important altruistic consideration. Although many of us could survive infectious disease for which we receive a vaccine, such as a flu, This is not true for everyone. Some individuals cannot receive the vaccine, for example, the very young or immune compromised, and vaccination is never 100% effective. In other words, the susceptible non-immune individuals among us can benefit from the passive immunity of their neighbors. However, there is a darker side to the eradication and the end of universal vaccination. Over time, the number of people with no immunity to the disease will begin to rise in the herd immunity. Vaccination for smallpox largely ended by the early to mid 1970s, leaving well over half of the current world population susceptible to the disease. This means that smallpox, or a weaponized version, is now considered a potential bioterrorism threat. In response, new and safer vaccines against smallpox are still being developed today, most of which go towards vaccinating US military personnel thought to be greatest risk of possible exposure. In the United States and other industrialized nations, vaccines have eliminated a host of childhood diseases that were the cause of death for many young children just 50 years ago. Measles, mumps, chickenpox, whooping cough, pertussis, tetanus, diphtheria, and polio, once thought an inevitable part of childhood, are now extremely rare or non-existent in the United States because of current vaccination practices. One can hardly estimate the savings to society resulting from the prevention of these diseases. Aside from suffering and mortality, the cost of treat these illness and their after effects are sequels such as paralysis, stiffness, blindness, and mental retardation is immense and drops the cost of immunization. In fact, recent estimates suggest that significant economic and human life benefits could be realized by simply scaling up the use of few childhood vaccines in the poorest nations, which currently bear the brunt of the impact of the childhood infectious disease. For example, it is estimated that childhood pneumonia alone caused primarily by vaccine preventable streptococcus pneumonia and Haemophilus influenzae type B will account for 2.7 million childhood deaths in developing nations over the next decade if vaccine strategies in these regions remains unchanged. Despite the many success of vaccine programs such as the eradication of smallpox, many vaccine challenges still remain. Perhaps the greatest current challenge in the design of effective vaccines for major killers such as malaria and AIDS using our increased understanding of immune system plus the tools of molecular and cellular biology, genomics and proteomics, scientists will be better positioned to make progress towards preventing this and other emerging infectious diseases. A further issue is the fact that millions of children in developing countries die from diseases that are fully preventable by available safe vaccines. High manufacturing costs, instability of the products, and cumbersome delivery problems keep these vaccines from reaching those who might benefit the most. This problem could be alleviated in many cases by development of future generation vaccines that are inexpensive, heat stable, and administered without a needle. Finally, misinformation and myths surrounding vaccine efficacy and side effects continues to hamper many potentially life-saving vaccination programs. For some diseases, immunization programs might be the best or even the only effective defense. At the top of this list are infectious diseases that can cause serious illness or even death in unvaccinated individuals, especially those transmitted by microbes that also spread rapidly between hosts. However, vaccination is not the only way to prevent or treat infectious diseases. First and foremost is preventing infection, where access to clean water, good hygiene practices, and nutrient-rich diets can all inhibit transmission of the infectious agents. Second, some infectious diseases are self-limiting, easily treatable, and non-lethal for most of the individuals, making them unlikely targets for costly vaccine programs. These include the common cold caused by rhinovirus and cold sores that results from the herpes simplex virus infections. Finally, some infectious agents are just not amenable to vaccinations. This could be due to a range of factors such as the number of different molecular variants of the organism, the complexity of the regimen required to generate protective immunity, or an inability to establish the needed immunologic memory responses. One major breakthrough in the treatment of infectious diseases came when first antibiotics were introduced in the 1920s. Currently, there are more than 100 different antibiotics on the market. Although most fall into just 6 or 7 categories based on their mode of action. Antibiotics are chemical agents designed to destroy certain types of bacteria. They are ineffective against other types of infectious agents as well as some bacterial species. One particularly worrying trend is the steady rise in antibiotic resistance among strains traditionally amenable to these drugs, making the design of next generation antibiotics and new classes of drugs increasingly important. Although antiviral drugs are also available, most are not effective against many of the most common viruses including influenza. This makes preventive vaccination the only real recourse against many debilitating infectious agents, even those that rarely cause mortality in healthy adults. For instance, because of the high mutation rates of the influenza virus, each year a new flu vaccine must be prepared based on prediction of the prominent genotypes likely to be encountered in the next season. Some years this vaccine is more effective than others. If and when a more lethal and unexpected pandemic strain arises, there will be a race between its spreads and the manufacture and administration of new vaccine. With the current age of worldwide travel, present-day emergence of pandemic strain of influenza could dwarf the devastation wrought by the 1980 flu pandemic, which left up to 50 million dead. However, the eradication of infectious disease is not the only goal of the immunology research. Exposure to the infectious agents is the part of our evolutionary history, and wiping out all of these creatures could potentially cause more than good both for the host and the environment. Thanks to many technical advances allowing scientists discoveries to move efficiently from the bench to the bedside, clinicians can now manipulate the immune response in a ways never before possible. For example, treatments to boost, inhibit, or redirect the specific efforts of immune cells are being applied to treat autoimmune disease, cancer, and allergy, as well as other chronic disorders. These efforts are already extending and saving lives. Likewise, a clear understanding of immunity has highlighted the interconnected nature of body systems, providing unique insights into areas such as cell biology, human genetics, and metabolism. While a cure for AIDS and a vaccine to prevent HIV infections are still the primary targets for many scientists who study this disease, a great deal of basic science knowledge has been gleaned from the study of just this one virus and its interaction with the human immune system. He showed that vaccination worked, but he did not understand how. Some scientists believe that immune protection in vaccinated individuals was mediated by cells, while others postulated that a soluble agent delayed protections. The experimental work of Emil von Behring and Saburo Kisato in 1890 gave the first insights into the mechanism of immunity, earning von Behring the Nobel Prize in Physiology or Medicine in 1901. Von Behring and Kisato demonstrated that serum, the liquid non-cellular component recovered from coagulated blood from animals previously immunized with diphtheria, could transfer the immune state to unimmunized animals. In 1883, even before the discovery that the serum components could transfer immunity, Ilya Mechnikov, another Nobel Prize winner, demonstrated that cells also contribute to the immune state of an animal. He observed that certain white blood cells, which he termed phagocytes, ingested microorganisms and other foreign material. Nothing that these phagocytic cells were more active in animals that had been immunized, Mechnikov hypothesized that cells rather than serum components were the major effectors of immunity. The active phagocytic cells identified by Mechnikov were likely blood monocytes and neutrophils, which can now be imaged using very sophisticated microscopic techniques. The debate over cell versus soluble mediators of immunity raged for decades. In search of the protective agents of immunity, various researchers in the early 19th helped characterize the active immune component in blood serum. This soluble component could neutralize or precipitate toxins and could agglutinate, that is, clump bacteria. In each case, the component was named for the activity it exhibited: antitoxin, precipitin, and agglutinin, respectively. Initially, different serum components were thought to be responsible for each activity, but during the 1930s, mainly through the efforts of Elvin Cabot, a fraction of serum, first called gamma globulin, now immunoglobulin, was shown to be responsible for all these activities. The soluble active molecules in the immunoglobulin fractions of serum are now commonly referred to as antibodies, because these antibodies were contained in body fluids known at that time as the body humus. Immunologic events they participated in was called humoral immunity. The observations of von Behring and Kit Shadow was quickly applied to clinical practice. Antiserum, the antibody containing serum fraction from a pathogen exposed individual derived, in this case, from horse, was given to patients suffering from diphtheria and tetanus. A dramatic vigilante of this application is today there are still therapies that rely on transfers of immunoglobulins to protect susceptible individuals. For example, emergency use of immune serum containing antibodies against snake or scorpion venoms is a common practice for targeting bite victims. This form of immune protection that is transferred between individuals is called passive immunity because the individuals receiving it did not make his or her own immune response against the pathogen. Newborn infants benefit from passive immunity by presence of maternal antibodies in their circulation. Passive immunity may also be used as a preventive prophylaxis to boost the immune potential of those with a compromised immunity or who anticipate future exposure to a particular microbe. While passive immunity can supply a quick solution, is short life and limited as the cells that produce these antibodies are not being transferred. On the other hand, administration of a vaccine or natural infections is said to engender active immunity in the host, the production of one's own immunity. This induction of active immunity can supply the individuals with a renewable long-life protection from the specific infectious organism. Here I have mentioned some of the important discoveries in the immunology for which Nobel Prizes were awarded. The Nobel Prize was started in 1901 and the first Nobel Prize in Medicine and Physiology was awarded to Emil von Behring, who is from Germany, for development of serum antitoxins against diphtheria and tetanus. In 1905, Robert Koch, who is also from Germany, was awarded Nobel Prize for Cellular Immunity to tuberculosis. In 1908, Eli Mechnikov from Russia and Paul Ehrlich from Germany were awarded Nobel Prize for their discoveries of role of phagocytosis and antitoxins in immunity. In 1913, Charles Richard from France was awarded with a Nobel Prize for the discovery of anaphylaxis. In 1990, Julius Bordet, a Belgian scientist, was awarded a Nobel Prize for the discovery of complement-mediated bacteriolysis. The most important and milestone discovery of human blood groups was made by Karl Landsteiner, for which he awarded Nobel Prize in 1930. In 1972, Rodney R. Porter from Great Britain and Gerald M. Edman from United States were awarded Nobel Prize for providing chemical structure of antibodies. many more Nobel Prizes awarded for immunological research, but it is not possible to mention all those in this single video. So if you visit this site of Nobel Prize, then you will find the list of scientists who received Nobel Prize in immunology. So I think you have enjoyed this video, and this video may be beneficial to you for understanding the concepts of immunity. So friends, if you like this video, then subscribe it, like it, comment your comments in comment box. Your subscriptions are very important for us, which motivate us to make such videos.